Dinesh. This presentation is based on material from Neural Networks and Deep Learning by Professor Andrew Ng from Coursera. I've also used other material from the internet. In this presentation, I'll be discussing gradient descent optimization techniques. Particularly, I'll be discussing about momentum method, RMS prop, ADAM, and learning rate decay. So before we get into gradient descent optimization techniques, I would like to quickly go over how gradient descent works in neural networks. We've already seen that in presentations 2, 3, and 4 that whenever we change the weights on the input layers, then the loss results in a corresponding change. So the whole idea behind gradient descent is how do we change the weights such that it results in the lowest loss. So how can you get the optimum set of weights? And this typically follows what is known as the forward propagation cycle, where we take the input features, use the weights, compute the activations in each of the hidden layers, and compute the loss. And then we take the gradients in the backward direction, which is how the loss varies with respect to the weight, and how the bias how the loss varies with respect to the bias. And we go through one cycle of backward propagation, and at the end of the cycle we compute the new weight based on the earlier weight and with a value known as alpha, which is the learning rate, and how the loss varies with respect to the weights in each of the layers, and how the bias varies how the loss varies with respect to the bias in each of the layers. And we compute the new weights and the bias, and then we use this new set of weights and bias again for the next cycle of forward propagation, and then go to the backward propagation. So this is a cycle. It goes through the forward propagation and then backward propagation. We compute the new set of weights and biases. Then we go through another cycle of forward propagation where we compute the activations and the loss, and then we compute the gradients and the new weights and bias, and keep going through this. So this is the regular vanilla gradient descent. Typically what happens is, when we do this regular gradient descent and iterate, the cost keeps dropping, but it oscillates its way towards the local minimum. What this presentation is going to discuss is how we can speed up this movement of this gradient descent in a fashion that accelerates the movement towards the minimum. So these are the gradient descent optimization techniques, and to understand these techniques we first have to understand what is exponentially weighted average. And in fact all this momentum, RMS prop, and ADAM use this technique known as exponentially weighted average, which is nothing more than a moving average. So for example, if we had a sequence of values, which could be any value, let us say temperatures or cost, or it could be gradients or anything like that. Let's say the values are sequence of values of theta 1, theta 2, theta 3, and theta t, a time series of values. Then the moving average at any point in time we can compute as follows. Let's assume the value at b0 is 0, and the moving average at point 1 is, there is a weighting value of 0.9 of the previous value, plus 1 minus 0.9, that's 0.1 of the value at this particular point in time, that is theta 1, and b2 will be this weighted value 0.9 into the previous value b1 plus 0.1 the value at that particular point, which is theta 2, and b3 is equal to 0.9 v2 plus 0.1 into theta 3. So we can go on like this. And so basically at any point, let's say bn, we get the moving average for this particular series of values, theta 1, theta 2, theta 3 up to theta t. So if we plot this, you will find it kind of follows how the values vary pretty closely, and though it's a bit wavy. Okay, so that's how you get a moving average, and it follows through how the sequence of values actually changes with time. Again, we can see that this is of this form, that is v1 is equal to 0.9 v0 plus 0.1 theta 1. It can be written as the value at any point vt is a weighted value we use, which is beta, into the previous value vt minus 1 plus 1 minus beta into the value at that particular point which is theta t. So this is the basic generalized formula for this. Vt is equal to beta vt minus 1 plus 1 minus beta theta t. And essentially what, when you use the value of weighting factor of beta, it essentially averages over 1 by 1 minus beta values. So for example, in our previous example, we use beta as 0.9, and so it basically 1 by 1 minus 0.9 using this formula is 10. So it kind of averages over the previous 10 values, and this is the green curve which we saw before. It kind of almost follows that. And if we use beta equal to 0.98, then 1 by 1 minus 0.98 is 15. So it averages over the last 50 values. So beta is equal to 0.98 is this purple line. So you can see that it tries to average over the last 50 values. So it doesn't quite follow with the current value, and there is a certain latency, so it goes like this and it's kind of shifted. Alternatively, if we had used a bigger value of beta, let's say 0.5, then 1 by 1 minus 1 over 0.5 is equal to 2. So it just averages over the last two values. And what happens in this is this red curve. This is kind of it's too squiggly, it changes very rapidly. So this is basically the moving average. So this beta is a very key value, a parameter in this exponentially weighted average. And so what does this exponentially weighted average do? So again, assuming we have this generalized formula, which is Vt is equal to some value beta of the previous value Vt minus 1 plus 1 minus beta into the value at that particular point, which is Bt. So here what I just actually substitute some values. Assume we have the at the 100th point, v100 is 0.9 of theta of 99 plus 0.1 v100. So if we and v99 is 0.9 theta 98 plus 0.1 v99, and so on. So once we expand this, we will find that this is of the form 0.1 v100 plus 0.1 into 0.9 v99 plus 0.1 into 0.9 squared v98 plus and so on. So basically you will find that each of these values v100, v99, v90, v97 are multiplied by a factor. Here we have 0.1, 0.1 into 0.9, 0.1 into 0.9 squared, 0.1 into 0.9 cube. So it kind of it keeps on increasing. And if you plot this, what happens is it's an exponentially decaying curve, and basically this curve falls to almost 1/3 of the value, and within 1 over 1 minus beta, that is within, for 0.9 beta, it kind of decays to 1/3 of its peak value. And so even though it takes in values earlier than this, it basically, the bulk of the value is the last the first 10. So it averages over the first 10 values. So let us look at the different gradient descent optimization methods. The first is learning rate decay. Then we have the momentum, RMS prop, and Adam. So learning rate decay. What is learning rate decay? In batch gradient descent or mini batch gradient descent, with each iteration, or in the mini batch gradient with each epoch, the the algorithm, the gradient descent algorithm, kind of oscillates across the ravines. If you assume, or if you visualize a kind of a valley or a trough, the gradient descent kind of bounces off the walls of the ravine as it makes its way towards the bottom or the minima of that valley. What happens is, if you use a fairly large learning rate, even though it approaches the minima, it can wander around that minima for a fairly long time, and because the learning rate is a bit too large for it to actually reach the local minima. So what the learning rate decay does is, the learning rate alpha is slowly decreased with the number of iterations or number of epochs. If we used batch gradient descent, we kind of decrease the learning rate with each iteration, and if we used a mini batch gradient descent, we would slowly decrease the learning rate with each epoch. And so basically, as we approach the local minima, we take smaller and smaller steps. So essentially we will tend to converge into the minima. So that is the learning rate decay, and that is one technique of gradient descent optimization. So the different techniques of implementing this learning rate decay. So these are all it's kind of obvious. The exponential decay is basically alpha is equal to decay rate into epoch num, so into alpha 0. So you just choose one decay rate, and as you increase the epoch number, this alpha will slowly keep decreasing. And this is second one, 1 by t decay alpha is equal to, with some initial decay rate alpha 0, you have choose some decay rate into epoch number. So as this epoch number increases, you will find this value actually decreasing. So this is another method where with epoch num or the number of iterations, you can slowly keep decreasing this learning rate. The next kind of gradient descent optimization technique, which is very popular too, is also known as the momentum method. So in stochastic gradient descent or batch gradient descent with momentum, what happens is, let us assume this is our gradient descent and we have a trough or a valley. The gradient descent will actually bounce off these walls of this trough. So it can come here and then it can oscillate here, and from here it will bounce off here. So it will keep on slowly going. So you can see that it takes this values, it kind of oscillates in this direction. What momentum does is, we use this exponentially weighted average or the moving average of the gradients, and so which will essentially follow this curve. The moving average will follow this curve, and actually it will tend to go faster towards this local minimum, as we saw in the exponentially weighted average technique, and that is essentially what is used in momentum method. So if we have dl by dw and dl by db is the gradients at a particular layer L, where dl by dw is how the loss varies with respect to the weight in layer L, and how the loss varies with respect to the bias in some layer L. Then this formula, if you notice, it is an exact replica of this formula which we had seen here, this formula. So this momentum is essentially that the moving average of the gradient at any layer is the value weighted average factor beta into the previous value, and 1 minus beta into the value at that particular point, that is dl by dw. And similarly, v db is equal to beta v dbl plus 1 minus beta dl by db. So once you have this values of v dw and v db, we use this new moving average of the gradients with respect to the weights and the gradients with respect to the bias, and then we perform the gradient with this weighted average. So we iterate as wl is equal to wl minus alpha of v dw instead of just dl by dw, and bl is equal to bl minus alpha of v dbl. So v dw and v dl w and v should be db are the momentum terms. RMS prop is another technique for gradient descent optimization, and RMS prop, basically what it does is, it basically damps the oscillation that is perpendicular to the direction of the minima while accelerating the motion towards the minima. So basically, if there's an oscillation on the either side of the ravine, it will average out and cancel those, whereas it will accelerate towards the minima. So that is what RMS prop does, and this is also further use the same technique of the moving average. Only difference is in RMS prop, which stands for root mean square prop. We define the moving average is SDW is equal to some weighting factor beta 1 SDW plus 1 minus beta 1. Here we take the square of the gradient dl by dw the whole square, and SDB is equal to beta 1 SDB plus 1 minus beta 1 dl by db the whole square. And when we are actually doing the gradient descent, we do WL is equal to WL minus alpha, the learning rate, into this RMS prop term SDW, and we also divide by the square root of SDW plus a value epsilon. That is basically epsilon is added to avoid a division by 0. Similarly, BL in any layer L is the bias in the previous iteration minus the learning rate alpha and the RMS prop term for the bias SDB divided by square root of SDB at the layer L plus eta, where SDW and SDB are the RMS prop terms. The third method is the adaptive moment. That is the first adaptive or ADAM it's called. And the first moment is basically ADAM is basically a combination of both the momentum method and the RMS prop. And so it uses the first moment is basically we do what we did for the momentum. VDW is equal to beta 1 VDW plus 1 minus beta 1 the gradient dl by dw, and VDB is equal to beta 1 VDB plus 1 minus beta 1 dl by db for the layer L. And this is a bias correction. B corrected dw is equal to VDW minus 1 minus beta 1 t, and V corrected dB is equal to VL dB by 1 minus beta 1 t. And the second moment we do what we did for RMS prop. So basically we do SDW is equal to beta 2 SDW plus 1 minus beta dl by dw the whole square, and SDB is equal to beta 2 SDB 1 minus beta 2 dl by db the whole square. And S corrected, basically this is basically just a bias correction for this SDW and SDB. And ADAM, basically we combine both the first and second moments. That is, we take the first moment, that is the momentum, that is VDW and VDB. That is we take the B corrected and V corrected DB. So we have the B corrected DW and V corrected DB, and we divided by the second moment, that is S corrected DW and S corrected DB. So S corrected DW and S corrected DB, and again we add this epsilon to prevent a division by 0. Okay, thank you, and that ends presentation 7.